All right, people. So we want to go through as many past papers as possible. We're coming live from UE Mona campus. Here with some Campion students. Campion students, say something. All right. So if you're watching this in the future, right before the exam, you know the drill. Just skip ahead a little bit because we're about to run through as many past papers as we can. So we'll be looking at the solutions, and anything you all see or you guys see, you can stop me and we'll go through the reasoning behind it, right? So let's just jump right at it. Paper 2 work solutions. We will start from 2020. If you hear any noise in the background, that's because my friend here turned on some Lasco fan here. I'm making some noise, right? So it probably not coming through. So let's get ready to cook. All right, so we're skipping all the question ones for now. We'll come back to some question ones near the end, right? Question ones with the graph and stuff. We do enough of that. So let's just jump straight into question 2. Define each of the following terms. Specific heat capacity. Let's go. How would you define specific heat capacity? So every time we come across a topic, we'll want to go through like the little mind map surrounding it. So specific heat capacity, S8C, sometimes it's called that. Specific, the word in maths and science, when you see specific, what does that tell us? Specific heat capacity. Why did they use the word specific? Because there is something called 8C, heat capacity. What's the difference? Yes, per unit mass. So this specific here means per unit mass. So if we're getting the energy, we can create an equation with specific heat capacity. Which one is given the small c, which one is given the big C? So the small c will get for specific, big C will go for capital C, heat capacity. So you'll say MC, small c, delta T. What does the T stand for? So the delta T means changing, or you have E is equal to M, no M, C, not small c, capital C, delta T. No M this time. Understood? What's the additional mind map in that? You should know about the units. So you should know the units of C and the units of capital C, which can be found by just watching capital E here stands for energy, which is in joules. And if I bring across the M, which stands for kilograms, I'll end up dividing by kilograms. So I'll have kilograms per kilogram. And if I bring across the temperature, what is unit of temperature? So that's per Kelvin. So this is the unit of specific heat capacity. If we want the unit of heat capacity, what we do just remove from this? The kilograms. So this is the unit of just heat capacity. Everybody press like on the stream, share it up, or feel free to share it up with your friends and whatnot, right? Let me go. So, okay, that's the mind map there. Specific heat capacity of a substance is the amount of heat energy. So that's a key part here. The amount of heat energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. You can put Kelvin here, same thing, without a change of state. So that's the full definition. Everybody could practice writing it for themselves. See if you can write it over again without watching, you're doing the active recall. See if you could get the key points. What is the specific latent heat of fusion of ice? What is that? Again, some mumbles there. So latent heat of fusion, what does the word latent mean? Hidden. And what does this tell us? Hidden in terms of what? Specific latent heat of, yes, so temperature remains constant, is correct. Fusion, vaporization. So there's two. There's one for fusion and there's one for vaporization. So you'll see a L with a what? A little F like this, or L with a little V like that. And yes, I'm still in Jamaica. So specific latent heat of fusion, this deals with fusion, you're thinking solid to liquid, right? Or vice versa, actually. Well, here's the thing. When something is going from solid to liquid, the temperature wouldn't change. It will be held at the melting point. So specific latent heat of fusion deals with the melting point. And latent heat of vaporization, this is going from liquid to gas or vice versa. So this deals with which point is this? This is your what? Boiling point. And finally, the equations. So the equations once again deal with energy. So E is M included? Yes. Yes. M is actually the only thing that they actually, because there's no change in temperature. So it's just MLF or E equal MLV. Everybody understand? So that's your mind map when you're dealing with latent heat of fusion or vaporization. So let's go back to the question. Specific latent heat of fusion is the amount of heat energy required to change 1 kilogram at 0 degrees, 1 kilogram of ice at 0 degrees into water. Yeah, man, bless. Into water at 0 degrees Celsius without any change in temperature. So how would you modify this definition if you wanted latent heat of vaporization? How would you modify this definition? What's the vibe? I just greeting some students here.
Been 4 years in the service, you said never pass so much in subjects.
So how do you modify the definition if they want latent heat of vaporization? You would change out the ice and put liquid water into steam, right? And then you would change the temperature at 1 and put 100 and keep it at 100 there. Right? So from liquid to gas changes to 100 because it doesn't have no change in temperature. Cool. A block of ice which has a mass of 2.5 kilograms and a temperature of negative 10 degrees Celsius is placed in a container. And what do they want? Specific, they give us a whole bunch of things. Calculate the heat energy required to change the temperature of the ice at 10 degrees Celsius to 0 degrees Celsius. So there's a few different ways these questions can come. Let me help you paint this picture now. All right, everybody, share it up, share it up. How can these questions come? Well, you can get maybe this start with ice, then you change it to water. That's a water droplet they are trying to draw. Water, liquid water, I mean. So start with ice, solid. Change to water, then you, from 0 degrees Celsius, this is 0 degrees Celsius, you heat it all the way to 100 degrees Celsius. So the liquid is hot now, and then you change it into gas. And they can make you work out the energy required for that entire process. They can do a question like this, where they just keep it in one state. Are they keeping it in one state? Let's see. What are they doing? Wait, that was from yesterday. It's going from, yes, it's one state, so it's still ice. So if you're not seeing a change of state in the question, which equation will you use? It's not changing state. Which one? I'm not hearing what they're saying. Oh, MCAT, say less. All right, so yeah, MC delta T, which they are calling MCAT. All right, yeah, MCAT it is. So use MCAT and just figure out this then. E equal MC delta T. 2.5 kilograms, negative 10 degrees. MCAT. So equal MC delta T, the change in temperature was what? The change in temperature was 10, right? From 10, negative 10 to, this is 10. M was given as, you have to watch out for any tricks here, 2.5 kg. Is this in kgs? It is. So 2.5 kg, and C was given as 4.2 times 10, specific heat capacity of ice. 2.1 is different if you're dealing with ice. 2.1 times 10 to the power of 3. Malik, what is it? 2.1 times 10 to the power of 3. So this was a little different. 2.1 times 10 to the power of 3 joules per kilogram per degree Celsius. And what do we want? The energy. So it's just a straight multiplication. What are we going to get here, everybody? Anybody have any answers yet? So you have 2.5 by 10. Campion, any answers yet? 2.1 times 10 to the power of 3. 5 to what? 5,500. 52,500, and this would be in joules because I'm seeing joules here, right? All right, let's see if we got that. Yep. And now they want the heat energy to convert all this ice to water. So we'll need this specific latent heat of fusion of ice, which is 3.3 times 10 to the power of 5. So latent heat of fusion is 3.3 times 10 to the power of 5. And this is joule per kilogram. So if I want the specific latent heat of fusion, the energy for that, I'll put MLF. So this is just a straight plug-in now, the MLF. And then, since I say MCAT, I'll pronounce this one too, then. MLF, all right, MLF. So this will be 2.5 by just straight 3.3 times 10 to the power of 5, which is, Malik is saying 825. All right, and this will be joules. All right, are we cooking? Okay, so we're going up bit by bit. We just started. Let's see if we could get this live up straight up to the top. I started late today. Where are we? You can also write it this way. The water in the container is now heated. So what you're noticing about this question is that they're breaking it up into parts. In the exam, be prepared if they give you the entire thing to do all at once without breaking it up. Like they tell you to calculate the energy to change it from negative 10 straight up all the way till whatever. So you'll just know to do it all together, right? All you understand? Yeah. So calculate what they want. The water in the container is now heated to a temperature of 80 degrees Celsius by an electric heater in 600. So they want the power. So before I find the power, what will I have to find? The energy. So the energy to heat it up from 0 to 80. Which formula are we going to use? We're going to use E, or we can just do it straight like what this person is suggesting. Kels is suggesting to just do it straight. You can do that as well. So E is equal to MCAT, MC delta T. So this is 2.5, and what we had, 4.2, was it 4.2? Let's go back and find it. 4.2 times 10 to the power of 3. And the change in temperature is 80 because it went from 0 to 80. So what's the number you're getting here for this? 2.5 by, this is the specific heat capacity, 4.2 times 10 to the power of 3. And then you have your temperature, 80. That's your temperature change because it went from 0 to 80. So Malik is saying 840000. Is that correct? Yeah? Well done. All right, so the number's starting to climb up. We're going up and up and up. And this is not the answer. The answer wanted power. But what is the relationship between power and energy? So power is the energy divided by time. So the rate at which you do the energy. So power is like rated energy. In maths or physics, anytime you see the word rate, that means over time. So power is the rate for energy. So we're going to put 840 000 over the time was something seconds, 600, or what was it? 600 seconds, right? So you put 600 seconds now, divide by 600, cross, 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 and how much you get? How much you got? 1,400 watts. The unit of power is watts, right? Watt. So this is assuming no energy loss, and then E equal PT, or P is equal to E over T. So 1,400 watts. Are we cooking? State one assumption which must be taken in account. CI, we already kind of state the assumption. We assume there's no energy loss. We assume all the energy that the heater is putting is going into the water. Everybody understand how to collect all 15 marks in this question? Yeah? 100%? So if they gave you a question like this now, so this one is for you guys to do, since you understand 100%. If they give you a mass of what? A mass of ice, and the mass of ice is, hang on a second, what do they have? Joules per kilogram. So the mass of ice is 3,500 grams, and they want to know how much energy is needed to take this block of ice and change it completely into steam. How much energy is needed for that? And they give you these constants. LF, what was the LF? LVC, C is 4.2. Let's go find them. Say they give you this as 3.3 times 10 to the power of 5 joules per kilograms. LV some kind of million or some kind of thing. So 2.26 times 10 to the power of 6 joules per kilogram. Go. And C is 4.2. By 10 to the power of 3 joules per kilogram. Let's try this a little better. Joules per kilogram per degree Celsius. So everybody try to do this question real fast. I will do it a shorthand method just now. So this started from 0 degrees Celsius, and this is 100 degrees steam. How do you change a block of ice at 0 degrees Celsius to steam? The energy for that. Proceed. You're going from ice to water to steam. Don't talk it, do it as fast as you can. You could quickly scribble it. Don't talk it, do it. So the total energy would be the sum of the energy got by the fusion part, which is ice to water at 0 degrees. Then you'll have to add the energy still in water, all the way to water, but you're going from 0 degrees to 100 degrees. Then you have to add the energy to change from steam, from water to steam. Water to steam at 100 degrees. Yep, so it's these three. So this is usually the worst case scenario for these types of questions, where you have all three involved. Other tricks in these questions is to watch to make sure your grams here, you see this in grams, so you'll change this to kilograms. So you just have to watch and make sure that the units match up. Sometimes they might have kilojoules or grams or kilograms or joules, and you have to make sure that what you're starting with matches up. Once you capitalize on all of that, you're safe. The first one is MLF, the second one is MC delta T, MCAT, and the next one is MLV. So it's going to be 3500, but this is really 3.5 kg. So everybody did that and didn't make any mistakes there, right? So I'll have 3.5 kg by all of these things being multiplied. The first thing would be the LF, which would be 3.3 times 10 to the power of 5. The next thing will be C and delta T. That's 100. 100 times this guy. 1, 2. So I can say 420 times 10 to the power of 3 plus LV, which is 2.26 times 10 to the power of 6. So for the sake of time, I'll go on. Kristen and Malik have the answer here, which is 1.05 times 10 to the power of 7 joules. So y'all could double check that. Don't forget the final temperature. I put it in here, I multiply this by 100. So MC delta T. So this is multiplied by 100. So this is 4.2 times 100. All right, so we're cooking. So once you all understand that, you should be pretty safe for this question. Let's keep going. So that's your full 15 marks there. That's a nice look at specific heat capacity. Next question is linear momentum. Momentum and moments are confused parts of physics. Let's try not to confuse them. What is the difference with moments? We were doing moments yesterday. So no, not in the direction of the force. That's work done. So there's a both of them have the same units. It's a very interesting thing. Not to be confused with work done. Work done is another name for what? Energy. Yeah, so this is AKA energy, right? And energy is measured in. So this is also known as energy. Apparently I can't write energy, it keeps scratching off. Which is measured in joules. And work done is force times distance moved as well. So it's the same FD. Moments is FD and work done is FD. But moments is not energy. Moments is something else. That's a turning effect. So what is the difference here? Well, with work done, it's like if you have this block and you are pushing the block in the direction of the force, you are doing work. So it's force in the same direction. So they are parallel to one another. Moments, there's a force that's being acted on an object involving a pivot. So the line of action of the force is perpendicular to the distance from the pivot. Everybody understand the difference there? So they are perpendicular to each other here, but they are parallel to each other here. So this one is Newton meter, but this Newton meter does give you joules. This one is also Newton meter, but this can't give you joules because they're not spatially oriented the right way. All right. So yeah, we are talking not about any of this. We are talking about momentum. Momentum deals with what? What is momentum? product of mass and velocity. So it's a body contains momentum when you examine the product of its mass and its velocity. So let's see what the question was. Defining linear momentum is defined as the product of the mass of an object and its velocity. So once you hit them that, you're good to go. All right, we're climbing up. We had a late start. Let's see if we can climb up all the way. Let's see if we can get in everybody here. So linear momentum is defined as the product of the mass of an object and its velocity. Now the symbol, it's useful to know this because they love to ask this. The symbol for moments is momentum is a P. What's the symbol for moments? Right, it's sometimes a T or sometimes a M. Most books have T. I need to go and check the syllabus and see what they want. But a lot of places have M. CXE used M already. So syllabus, I think it has T though. I can't remember. So momentum is P. All right, where are they going with this? Oh, by the way, when they ask to define something, if it's 1 mark, well, the definition should work. But when they ask to define something, you should always write the formula one time. So P is equal to mv. M is in kilograms. V is in meters per second. That's velocity. So P is kilograms meters per second. We cooking so far? All right. Mr. History, you good? State the SI unit for linear momentum. Well, we already established that, kilogram meters per second. State the law of conservation of linear momentum. So this will be the usual flow of the questions in the exam. If they give you the definition, they give you the units, they want to know the conservation of momentum. So everybody knows that? In the absence of external forces, the total momentum of a system of body is constant. So this is one way of stating it. Maybe you know it. Total momentum before collision is equal to total momentum after collision. That should work. But this is a more complete definition. State 2 real-life examples that demonstrate the law of conservation of linear momentum. Right.
Wait, sir, why did you say I'm going to recoil now?
Why did I say what?
You said I'm going to recoil that you should put that. I recoil my gun.
When did I say that?
You said it once, I heard you say that.
Yeah, I said that. Well, I said that last night?
No, like, you know, different.
Oh, yeah. But I did say that because in CXE, they normally deal with collision and not explosions. But explosion, total momentum before explosion equal to total momentum after explosion too. But use examples what they use, like the billiard balls, or pool ball, or marbles, or a really good one is what Malik is putting there in the chat. Well, yeah, cricket ball and bat from the crash course. Cricket ball and bat and Newton's cradle. You all know what the Newton's cradle is? The Newton's cradle is that toy that, yeah, just been knocking. You know what I'm talking about? The toy that where this thing will knock this and send this one up and send it back. All you know what I'm talking about with the Newton cradle? So yeah, these are the 3 examples that you use here, people. Not 3, 1, 2, 3, 4, 5, if they ask you. All right, 5.
So, sir, what time is it? Oh, sorry,
Trolley A and trolley B collided head on. All right, so like they're giving you trolleys as the examples here. Calculate the initial momentum of trolley A. What is something that you need to watch out for when you're doing this? The direction, very good. So the direction is key in these types of questions. So you need to set one as a direction, set one direction. Did I do this yesterday? Set one as a direction and then move on. I feel like I did it recently, maybe with my class. So let's see how we'd extract all the data from this question. Trolley A of mass, so let's pick trolley A was moving towards the west. So towards the west is this direction. This is west. So what's the east is this direction. By default, which one you all will put as positive? So I will usually put east as positive. Let east be positive. So west is negative, east is positive. So if we delimit trolley, A, what do we write? What do we know about trolley A? We know its mass. So M is 72 kg. We also know its velocity, 5.50, but it's moving to the west. So what would you put next to that 5.50? Negative 5.50 meters per second. And then what do we know about trolley B? We know its mass as well. Both of them are the same mass? No, a little less. 69.4. And the velocity is how much? 4.5. And do we put a negative next to this one? All right, because this one is going in this direction, to the east. This one is going to the west, right? And the question probably wants the initial momentum, 3 marks, 2 marks. So the initial momentum for A, so what they're doing is they're gonna break it down for you. You combine both momentums and then you get it. But they could probably give you the whole question all at once. They could give you the whole question all at once, right? So the momentum, you could say PA is gonna be MV, MA, which is how much? 72 times negative 5.5 is? And PB is 69.4 times 4.5, which is 3,000. So you get 396. That'll be negative 396. And the other one is going to be, so negative 396, and you put kilogram meters per second. What you all got for the other one? See? 312.3. 312.3. I saw some person put that in the chat. Meters per second. So are we cooking? Yes. Boom, bang. Assuming the trolley is locked during the collision and then they move off, determine the speed and direction of the joint trolleys immediately after collision. So we could get how much momentum is in the system right now. What is the momentum, total momentum before collision? What is the total momentum before collision? We just add the two together, right? Negative 396 plus 312.3 is negative 82.7. Hey, negative 83.7 kilogram meters per second. And therefore, this has to be the same momentum after collision. So this is momentum after collision is also negative 83.7 kilograms per meters per second. Yes? And then what does this mean for us? How do we work out the velocity? Well, we agree that therefore the momentum after collision is equal to the momentum before. But we need an equation. So we need like the MT and the V is equal. This is what we want. Is equal to this negative 83.7. This is the V we're trying to find. What is the MT about? Because momentum is mv. So this is our total mass. So this is what? This is, remember they locked together, so this is the 72 plus the 69.4. Which is how much? 0.4 V is equal to negative 83.7. So how do we find V now? We divide or transpose, right? So the V is equal to negative 83.7 and we divide by the 141.4 and how much you get? Negative 0.59. Now let's go check the question. Maybe they wanted it to some specific significance. They didn't say anything about. Okay, so let's say negative. Right, people explaining in the chat. Great. So negative 0.59 is what you all got. 59 what? 592. And this is meters per second. So what you're going to say is velocity, ignore the negative, is just going to be equal to 0.592 meters per second. And since you see negative, what direction does that mean? All right, to the west. Negative is west. And you collect your marks. All right. How was that? Any questions? This is another way to do it where you just equate everything one time, but we already know this answer, so we minus and then you bring it across and you get this. So the speed and direction, this to the west. Nice. Moving forward. The next question was the laws of refraction. What are your laws of refraction? Right, so both laws of reflection and refraction have the same setup. So with that, so what are your laws of reflection? So the incident ray, the reflected ray, I'll say reflection, I switch to reflection, and the normal are all on the. What does that mean? It literally means what it says. They're all on the same plane. So like if you shine something on this, it will reflect exactly on the same plane. You don't expect, like if I draw this in 3D, you don't expect something to be going like this and then reflect off in an opposite direction. You expect it to be on the same plane. So like I can draw another paper to this. That's where the reflection will occur on the same plane. It won't come off the plane. So, okay. That's a kind of obvious law. And what's the next law of reflection? Incident who? Angle of incidence is equal to the reflected angle. So better stated as the angle of incidence is equal to the angle of reflection. All right, but if we're dealing with the refraction, what are the laws of refraction? So we still have the same plane business where we have the incident, the refracted this time, and the normal all on the same plane. But what else? There's one more. And what is that called? So if you have to put this in words, how would you put this?
The ratio of the time of the incident angle to the time of the refracted angle is always.
Wow, that's very good. So the ratio of the sine of the incident angle to the sine of the refracted angle is always constant, and that constant is known as the refractive index. Refractive index. Cool. Cooking. So for here it is in a nice professional format. The ratio sin I over sin R is a constant for a given pair of media. That's just a fast way of saying that. where I is the angle of incidence and R is the angle of refraction. This is Snell's law, and N is, I should put N equals sine over sine R. N is known as the refractive index. Beautiful. So some diver went under the sea, shine a beam of light towards the surface of the water. The light does not pass through the water-air boundary into the air above, but reflects into the sea. State the name of the phenomenon which occurs and briefly explain why it occurs. And I hear you. Right. And why did it occur though? What was greater than the critical angle? Right. So the angle of incidence was greater than the critical angle. So we have that. The name of it is total internal reflection. And this occurs when the light travels from a more optically dense medium. So you should include that. So it has to go from a more optically dense medium to a less optically dense medium. So like glass to air, water to air. The angle of incidence of the light ray is greater than the critical angle. The light ray is completely reflected back into the water. Full marks, right? Another diver shines a beam of light into the water to see some fishes as shown. Okay. You do need thing. And we need to work out R then. Yeah, calculate the angle R. Everybody go real fast. So this is like one of the easier versions to this question. Calculate R. Let's go, chat. Let's go, let's go. So we have a 40.6 from the chat. Anybody else here getting 40.6 as well? So you just want to put N is equal to sine I over sine R. Literally, substitute this is equal to sine of I, which was what, 30? What's up? That's not. Change people asking me to do things and sine I was 30 over sine R, and was 1.33 or something like that. And you just rearrange, so you get sine R. Was it that? Yeah, 1.33. Oh, it was 60. It was 60. So you rearrange, and then you'll have to find the sine inverse. Everybody know to make the calculator talk like that, right? So I have it back to front here. Same thing. Bring up the sine R, bring down the 1.33. So you should end up in this situation, and R is the sine inverse of that. Now I would just go ahead all the way here and go R is the sine inverse and put this entirely into my calculator. And you should get 40.6 to 1 decimal place. No problems. No problems there, right, class? Everybody good? And then we go into this. As soon as you see this, what do you think you're going to do? This is the thing from yesterday. What do you think we're going to do as soon as you see this question here? Pressure. What are you going to do here? The lens formula, right? Lens formula. So you put 1 over F is equal to 1 over U plus 1 over V. Calculate the image distance V. So see if you all can do it real fast. Everybody see if you can do it. You're going to use that formula that Kels and Kirsten have in the chat there. 1 over F is equal to 1 over V plus 1 over U. This one here. Samantha, what's that one? So yes, that's another formula that comes in, but that formula that Samantha said there, that height of the image over height of the object, what is that formula about? Magnification. So answers, any answers coming in? 1 over F, calculate the, right, so 1 over V. So it'll be 1 over f minus 1 over u. Get that answer and then invert it. How much you got? 15. So it's going to be 1 over 6 minus 1/10, which is 2 over 30, 1 over 15. So then you invert that back again and you get 15. Ariana, you understand?
Oh, yes.
All right, you look like you're spacing out. All right, so V is equal to 15. Great. And then the linear magnification. So if V is 15 and U is 10, what is the magnification? You can just watch it and see. 1.5. So it's going to be image distance over object distance. So V over U, 15 over 10, 1.5. Ariana, you know Malik? Oh, okay. Well, he shout you out there. So V over U is 1.5. Marks, another 15 marks down. Anybody have any questions about this 15 marks? Nope. Good to go? Let's do a quick example again. So let's say we have the height of the image was 20. The height of the object was 20 centimeters. Excuse me. And the height of the image. What's that? Yeah, I'm still kind of coming up with it here. So what do we have last time? Yeah, so let's say we have the height of the object was 20 and the height of the image is 5 centimeters. Find the magnification. Magnification. And if the object distance is find not 15 centimeters, let's say the object distance is 10 centimeters, find the image distance. All right, so this question deals with it in reverse. See if you can get the answer. Find the magnification. You get 1.5. I'm saying that the object height, the height of the object was 20 centimeters, and the height of the image was 5 centimeters. Let's go. All right, guys, so we just started. Well, actually, class just started again like 40-something minutes ago. We went through some topics. So magnification is always V over U. In this case, you could say HI, height of the image over height of the object, high over who, which is 5 over 20, which is 0.25. What is the unit for magnification? There's no unit, so unitless. So the object distance is 10 centimeters. So find the image distance. What would you do in this case? The image distance. What is the letter for image distance? What is the symbol? We're trying to find V. Do we have U? U is 10. So U is 10, and we're trying to find V. Do we have F? No. So how are we going to find V? How do we find V in an instance like this? Use the magnification back again. So V over U is supposed to equal to the magnification. In this case, we know it's 0.25. So if this is 10, then what is V going to be? 0.25 times 10. So it's V is going to be 2.5 centimeters. And now can you find F? 1 over F. So you all understand how it could come in reverse, right? 1 over U plus 1 over V, and you cook with that. So you'll end up with 1 over, what it was, 10. Yeah, 10 plus 1 over 2.5, 1 over F. How much is 110 plus 1 over 2.5, or 2 over 5? 4 5s, a half. Tell me if you'll get a half. So F is equal to 2. So F is equal to 2 centimeters because you'll have to invert in the end. All right, people. Everybody clear on that, Crystal? Full marks if it come in the exam, right? All right, so back to logic gates again. This is a quick look at NOT, and there was an error in this question when it came. There was an error in the CSEC question here. So they described this badly. And then there is the circuit diagram. Describe how, so you see how it could come, the rectification for 5 marks can be halfway rectified to produce a direct current across a resistor load. So how are we doing this? If they ask to show with the aid of a circuit diagram, you use this. When the diode is placed in the circuit diagram, only half of the wave would be allowed through. This is called half-wave rectification. Half-wave rectification is the process of converting AC to DC by preventing 1/2 of each cycle from being applied to the load. Did this specify load? So yeah, you have the resistor load. You don't need to put in the ground or anything like that. So this diagram is a little too complicated for CXC. So you need to put in the AC supply. You would need to put in your diode, and you need to put it in your load, and you can put some kind of voltmeter or something to just measure what's happening there. Everybody understand? So I would include this diagram as well in my explanation and say what the diode does. So you need to explain what a diode will do. The diode only allows current or the EMF to pass in the forward bias. So it removes in negative half of the alternating current. So every half cycle is removed. This is called half-wave rectification. And then you can see the rest of stuff that we have here. Everybody good with this? Somebody say this is not coming. This is so simple. So I don't know why somebody trying to say they cooked with this. There's nothing to learn with this, just the diode, and it only allows current in one direction. This is the AC current. You cut off the bottom pieces, and you just explain that in your own words. There's nothing. This should come. It's 3 marks, 5 marks, right? Sketch the voltage time, or they ask you to sketch it after to show the expected output across the load. Here you go. So it's flatlining on the zeros where it should have gone below. It's like you take the AC current and you completely cut it off. Voltage time. Simple. 3 marks, ladies and gents. Draw a voltage time graph showing an AC source with 5 Hertz and a peak voltage of 12. So if they give you this, what is something that you'll need to calculate to be able to draw this graph? The period. And how would you work that out? 1 over the frequency. So period is 1 over frequency. So the period is what? Period in this case will be 0.2. 1 over 5, right? So that's how I got 0.2 here. And how did I get the 12? Well, it told me that. It told me it's going up to a peak of 12. So all I have is the 12 and the 0.2, and from that I'm able, well, this isn't drawn exactly. It should kind of cut through exactly through the 0.1, right? Everybody understand how we come up with that graph? Cool. Okay, so you're going into alpha, beta, gamma. This means we're in radioactivity. Draw the 3 rays to represent each part as it passes through the magnetic field. Okay, so we spent a lot of time on this last night. So let's just do a random one. We won't do that same one. Let's say CXC decides to put dots this here. And it's a magnetic field. By the way, dots mean in the paper or out the paper? Dots, are you watching the arrow or the back of the arrow? Front of the arrow, back of the arrow? For a dot. So to remember which one is which, the back of the arrow would look like the X's. The front of the arrow look like the point. So if you are seeing the front of the arrow, that means the arrow is coming out the paper towards you. So when you see these dots, it means out the paper. Sometimes they'll put that dot in a circle. And when you see the X, it means it's going into the paper. So is this going out or in the paper? This is going out the paper. So if I put a radioactive source here and I say, let's just do alpha. What would be the deflection of alpha? So we know it's not going to go straight through. That is gamma's job. So we need to determine whether it's going to bend up or down. Which hand are we using? So you're using Fleming's left hand, because Fleming's left hand gives us the motor effect, the motion. Motion is the answer. Now, I'm holding up my right hand in here, but it's my left hand in reality, right? So left hand, like this. This is what you're using, but you'll have to spatially arrange it so that what finger is going to point this direction? Since it's alpha, alpha moves in the direction of conventional current. Which finger is current? Middle. So point your middle in the direction of that arrow. Your index finger is going to point what? Up. And tell me which way is your thumb pointing in the end. Line it up with the I need to see you lining it up. Well, it's not right. You have to tell me it's going to up or down. It's going to go up. So it's going to go up. This is probably the most troublesome part for you. So the current going this way, you see my hands? And this going up, so my thumb is pointing up. This is going out the paper, so my thumb is pointing up. Right? So this is going to deflect up. And once you figure out alpha, gamma will go in the next, beta will go in the next direction faster, right? And actually curl backwards a little bit. This is the magnetic field. And then gamma is just going to go straight ahead.
So how did you say that? I know, like, if they give you a source and where alpha and beta is like on the left or on the right or something.
It doesn't matter. It doesn't matter whether they're on the left or the right. That's what you're actually trying to find. I did not decide to put beta here. I used Fleming's left hand rule.
I would just do alpha and
Yes, you can do that. Just do alpha and draw everything else afterwards. Gamma is unaffected. Everybody make sure and get a mark for gamma at least, please. So what happens again if we have, well, this one is easy. What happens if we have electric field and this is positives? Who goes to positive? Beta will go quickly to positive. Alpha will go a little slower to negative. Remember, it doesn't curl back at all in these diagrams for this one. And gamma will go undeflected.
So you said it doesn't curve for this one?
It doesn't go backwards. So in this diagram, you can actually show beta curling backwards. In this diagram, it doesn't curl backwards. It just goes straight to the plate. All right.
So it doesn't look much different from the alpha?
Yes, it is much different. It goes faster. So it does go faster, but it doesn't go backwards. All right. The magnetic field is replaced by electric field. We did that one already just now. So we have this. So shout out my channel, please. Nick Blue Nova YT. Or you can go and check out the channel. All right. So an unstoppable isotope of lead undergoes exactly 2 sequential beta particle decays followed by alpha particle decay to become stable lead. We did this, right? We did this yesterday, y'all remember? Or the 2 equations. So the transneutron went up, and then you lost back everything. But this one is stable, this one is unstable. Good. And that's the end of that exam. Let's check. So that was one paper done there, people. We skipped all the question 1. But so 2021 now, let's do it. Let's go another paper. Somebody say another one. We're skipping all the question 1s for now. Number 2, define moment of a force. We talked about that just now, so everybody's supposed to be able to cook. Why I can't move? Moment of a force. Moment of a force. Line of action. So I should hear line of action, I should hear pivot or fulcrum, and I should hear perpendicular distance. So moment of a force is the effect of a force about a fixed point. It is the product of the magnitude of a force and the perpendicular distance from the pivot to the line of action of the force, and it's given by the equation. What? This is 2021. I don't know. Let me see. June. 2021 June. Please learn this definition properly. I want to spend 2 minutes and just make sure you have the definition down. Because I finally have a real sketch, boy. Everybody make sure you learn this definition properly. So what would be some of the, if you want to have it word for word like what I have it here, right? Moment of a force is the effect of a force about a fixed point. So you start off with that. So effect of a force about a fixed point. We know we want to say line of action of the force. We know we want to say the perpendicular distance, and we know we want to use the word pivot. All those words we want to use. So we start off with, it is the product. What is it seen? Falling. These are, you know, these people? Yeah, what is it seen? It is the product of a force and the perpendicular distance from the pivot to the line of action of the force. So, all right, wait. All right, so we have our next table joining us. Make yourself at home, gentlemen. So it is the product of the magnitude of a force. I should say magnitude of the force, right? It is the product of the magnitude of a force. Now, if I don't say magnitude of a force, that's 3 marks still. The magnitude of a force and the perpendicular distance. And the perpendicular distance from the pivot to the line of action of the force. So from the line of action to the pivot. And it's given by the equation. And then if you see 3 marks, for sure you're going to throw that equation. And then M is equal to FD, or T is equal to FD, where F is Newton, D is meter. So therefore the unit of M is Newton meter. Everybody understand? Yes. Performance.
Wait, sir, so the 3 marks is the unit and the equation and the
Yes. But if they have to define, if you just put the definition, you are supposed to get the full marks. But I want you to practice doing everything. Just the words, but you're going to do everything. Just like how you're meriting history. Center of gravity. How do you define center of gravity now? Appears that, right? So the point in which the center of gravity can be defined as the point through which, so I'll change into through, which its entire weight acts for any orientation or seems to act from any orientation, or that's the other sweet spot it didn't let go. From any orientation of the orientation of the object. Learn it exact, learn all the tricks with it. The point through which the entire, so some of the words you left out there were, right, the point, we use the connector through which the entire weight.
Sir, did you put mass? Like when you're defining moment, what, like you wrote in the screen.
I didn't put mass.
What is that?
That's force. It is the product of the magnitude of the force and the perpendicular distance from the pivot to the line of action of the force. Yeah, that's MAG, magnitude of a force. So the point through which the entire weight of the object seems to act. And what's the last little piece? For any orientation of the object. All right. And then you try it again and you make sure you have it understood. Make sure you can repeat it without having to, without making any mistakes. The two conditions necessary for a body to be in equilibrium. From the time you see that, you know they're talking about static equilibrium conditions, which are what? Right, so some of the net forces is 0. And that was the next one? The total anti-clockwise moments is equal to the total clockwise moments. Now you write it out fully, right? So net forces acting on the body is equal to 0, and the sum of all the external moments about the axis must be 0. This is a shortcut way of writing it. Or you could say all the anti-clockwise moments about a point on the body is equal to 0. So everybody should be cooking this. This is not supposed to be cooking you. How prepared are you? You ready? Okay. Look out for your name on the merit list. What's your name? Matthew Spencer. I'll look out for Matthew Spencer on the merit list. So figure 2 shown below is a diagram of non-uniform wooden plank AB, which is 2 meters long, lies 1 with, it's non-uniform. So when you see non-uniform, what does that tell you? So we don't know where the center of gravity is, right? So you can't run that. Maybe we need to find that. C is the center of gravity. Okay, so they show you C and we're trying to work out C. Well, there's some helper lines here that already kind of gives you the idea. So this is like a worst case scenario moments question. I guess we need to find the value of X. So the plank is supported from a ceiling by 2 vertical springs P and Q. The plank is attached at a distance 0.5 from each of the end. C space is the center of gravity as shown in figure 2. Cool. The calculate the tension in spring Q. How would we calculate the tension in spring Q? Right, and what's the downward force? So what is the tension in spring Q really quick? You can just watch it and work it out right now. 500. Because you thought it was uniform, so you divide by 2, but it's non-uniform. So they say 1 is 600, so P is 600. So Q has to be 400. That's clean, right? 600, 400, 1000. So now that I know this is 400, I know this is 600, I can work out X. Everybody, I'm giving you all, including YouTube, 3 minutes head start. Try and work out X. You have everything that you need to work out X, because you know what P is. P was given. P is 600. Q is 400. W is 1000. So we're trying to work out X, the distance X. That was it for the question. Now I want you all to work out X. Determine the distance from P to C. from P to C. They want this distance here, but I want you all to work out X. Go ahead. So what you need to do, you need to take moments about a point. So you can either take moments about point A, about point P. If I were you, I would probably take moments about P, right? P looks like the better one to take the moments about, right? Oh, there's any questions are taken from me? Ah, okay. Zero 0.4 for X. X will be 0.4, probably 0.4 for the distance P to C, maybe. But I want you all to work out X, so maybe you just already worked out the distance P to C. So X is 0.9. Somebody in the chat getting the value of X. You also got 0.9? Who is that? Who also got 0.9 there? State your name. Ariana, you got 0.9? All right, so everybody getting 0.9. So if you go about A, the clockwise moments will be 1000 by X, and that's it. The anti-clockwise moments will be 0.5 by 600 and 0.4 by 2 meters minus 0.5, so 1.5 by 400. So let's see it. Let us see it. 1000 by X must be equal to 600 by 0.5 and 400 times 1.5. Everybody started off with that premise? Yes? And then you just work it out. So 300 plus 600, 900 divided, and yes, you get 0.9 very fast. So if X is 0.9, how do you find the distance from P to C? P to C. P to C. 0.9 minus 0.5, and you get a nice looking 0.4 cooking. So this is like worst case scenario. Everybody understand moments? You can do moments.
Wait, sir. So when it's in the middle, when it's uniform, I use the way to the actual middle. And that double force for the W right here.
What Burger King coming in here, boy?
The W right here.
I'll order that. Pops. We need to take a Burger King. Now we continue. So state why the center of gravity is located closer to point P than to point Q. Here's a nice way of saying it. There's more tension in spring P, which means that more of the weight of the plank is concentrated closer to P than Q. So the weight is more concentrated on one side. So that's why the center of gravity is shifted, right, Matthew? Matthew, what is this we're looking for again? Matthew, what's the last name? Spencer, yes, Spencer. Waves can be described as transverse or longitudinal. What is meant by a transverse wave? 3 marks. I find that you're not clean on the definitions and it worrying. Get clean on them definitions. Mr. Meritless, what is a transverse wave?
So a transverse wave is a wave whose particles travel perpendicular to the direction of the wave.
Okay. So the vibrations of the particle are perpendicular to the direction of the wave. What's a nice word for direction? Propagation. The man really know thing. So you might get the full marks there with that one. So it's one that has vibrations perpendicular to its direction or propagation. In other words, a transverse wave is where the displacement, so a displacement is another thing you could use instead of vibration, of the particles is at right angles to the direction of the travel of the wave. Great. Give one example of transverse wave. Light. Another one. You don't want to say radio waves because that on the same EMF spectrum, everybody's transfer. All EMF radiation is transverse. So light, if you say radio wave, that feel kind of weak. Water waves. So light and normal water waves in the sea, right? Transverse. What is ultrasound? Right? Frequency, not speed. So it's a sound wave with a frequency, not speed, right? Frequency that is higher than the maximum frequency that humans can hear. What is our range as humans? All right, Mr. Meritless, very good. 20 hertz, 20 kilohertz. State one example of ultrasound. Or one, I guess it probably should be one use of ultrasound. Machinery, too vague. Medical imaging, right? So like maybe to see the gender of a baby or something like that. Medical imaging is good. Figure 3 shows the path of a light ray from air through a cube of ice along with 2 rays showing partial reflection. Partial, right? Not total internal reflection. And we are required the angle of incidence on the phase MN. Can you get that, everybody? You will need to know, where is it? Was it given? You will need to know MNO. All right, let's see. So this is a common mistake that we have. You know, I was teaching sometime fast, and I think I made the mistake one time actually. When I was teaching, Malik probably was there for that session. I actually said 31, but this is 59. The angle of incidence is always between the incident ray and the normal. So this question was just asking you to say 90 minus 31 is 59. Then what was next? So 90 minus 31 is 59. The angle of reflection on the phase MN. The angle of reflection. So the angle of reflection will have to be equal. So angle of reflection here would be 59 as well. Not R, this angle. So the only dealing with reflection right now, angle of reflection on the phase MN, I is equal to R according to the law of reflection, right? The angle of refraction, and finally they gave you the refractive index. So since the refractive index is given as 1.31, are you able to find the angle of refraction? We just did something like that. So I'll speed through that one. Sin I over sin R. R is the unknown. Bring it across. Divide, find the inverse. 40.9. 40.9. And then label the critical angle theta for ice. So it seems like I'm getting that total internal reflection about occurs. It seems like this is exactly at the critical angle. So I'll label this as my critical angle because I'm seeing this line passing here. So they want you to label the critical angle. This is X. All right, I see about 30 more people popped into the YouTube live. Big up the 30 people who popped in here. The critical angle is the angle of incidence that makes an angle of refraction of 90 degrees. So you see that 90 degrees here? You see that you're all following the ray? It's now about to go into total internal reflection. So this is the critical angle. X, that's what they're asking you to label there. Cooking. Oh, that was it? They didn't even ask you to work it out. They probably run out of max. You know, TikTok always shelling out the max. But guys, if you needed to find the value of X, how would you find it? We got this as 40.9. This is a right angle. So can you figure out what this is going to be? This is just triangles. You say 90 minus 40.9 and you get a missing angle right there, right? Yes? Which would be 49.1 or something. 49.1. Angles in a triangle add up to 180. So if this is 90, this is 40.9, you can find the missing angle. So that would have been the value of the angle of reflection. Let's go. Are you come here to eat or to study physics? All of the above. On the figure 4 below, sketch the graph of pressure versus temperature in degrees Celsius for an ideal gas. All right, so let's go through the whole gas laws thing once again. Malik, this will be the last time you've seen it in a while, boy. Let's go. Why is my board frozen? There's big problems, you know. My board knock out. This will take a while for it to catch back. So how things looking for physics, ladies and gents? Other than Matthew Spencer, anybody else on the merit list? Let me just bring up this. Make sure y'all can sketch that graph. Go ahead and sketch this graph, people. Why is I trying to get my board to behave here? Otherwise, I had to end this whole stream. And we now starting to pick up a length now. Anybody happen to have a USB dongle? I think it's that it has a short. So you're gonna, I'll have a little 3 minutes break here while I try to get this thing to connect back. My board see gas laws and decide to call it quits one time, right? Only God can save me. All right, I feel you going to start back here now. I sense it. So let's do the whole mind map of gas laws. Everybody know about the gas laws? So how do you start off with gas laws? What do you do to like initialize your understanding of everything with gas laws? So the first thing you need to know is who is constant. What is held constant for each law? So in the Boyle's law, what is constant? Temperature. To help you remember that, boiling, temperature, constant, boom. Which one is different than the rest? Boyle's, Charles, or pressure? Which one is different? Which one is inverse? Boyle. So Boyle's is like first, so we deal with that first, right? So that's inverse. So since temperature is constant, the three things in all of these laws are what? P, V, and T. So if temperature is constant, that leads me to write pressure is inversely proportional to volume. Yes? Everybody could record that? And in the pressure law, what is constant? Volume, because in the pressure law, pressure is not constant. Pressure is like a responding variable. So pressure is constant here, volume is constant there. So these two are directly proportional. So proportional to temperature. So P is proportional to temperature, V is proportional to temperature. Everybody understand that those first two lines of the law and how you can get it back in the exam if they ask you? This is a relationship, right? This is not an equation. So if the exam says the word relationship between whatever, you'd use this symbol. But if they want equation, if you want to change it to equation, we're going to put in K. Like this. So far, so good? Pressure, what is the unit of pressure? What is the unit of volume? And unit of temperature? Kelvin, good. So if we want to get a combined version of all these laws, what would we use? So there's two ways to represent the combined version. One is more theoretical and one is more useful in questions. So N is equal to P V over T. So this is the more theoretical one where N is a constant. For a fixed mass of gas, pressure by volume over temperature is a constant. Or the one that you use in equations, Malik just put it in the chat there. P1 V1 T1 is equal to P2 V2 T2. So far, so good? So how does the graph look? It depends on whether it's in Celsius. Well, this one has nothing to do with Celsius. This one is just pressure and volume. So we'll ignore this one. This one is special. Pressure and volume. An inversely proportional relationship does a kind of exponential decay graph. So it looks like this. Everybody understand? How do they get the graph to turn into a straight line? What does 1 over V? Very good. So they put 1 over V here, and they get this to be a straight line. This happens in a question 1. So usually if they bring gas laws in a question 1, they'll zero Boyle's law and do this thing for you. And you'll have to plot a graph of P versus 1 over V, draw that straight line, get the gradient, and work out some stuff. The gradient of this line is not the constant. Gradient of the line will be 1 over the constant, right? Actually, this is P versus 1 over V. Yeah, so the gradient is the constant, K, because you have 1 over V. This is like if you have P is equal to K by 1 over V. The 1 over V is like your X. Y is equal to mx. Anyhow, let's keep going. The graph here has 2 versions. There's a version if it's degrees Celsius, this is temperature is in degrees Celsius, this is pressure. And then there's a version if the temperature is in Kelvin. So if the temperature is in Kelvin, you expect the graph to go like this. Why? What is that value known as? Absolute zero. Who said that? Next to Matthew, isn't it?
What?
What? Orange. Orange. Our next merit list study. Like orange? So this one would look like this. And this value here would be negative 273 degrees Celsius. So this one is 0 Kelvin. This one is negative 273 degrees Celsius. Same thing will occur here, you know. It's just that on this axis, instead, you will have, did I put P here? Sorry, this should be V. On this axis, you'll have V. So this will also be negative 273. And this one is going to be 0 degrees, 0 Kelvin. This is if your temperature is in Kelvin. All right, everybody understand this entire mind map of gas laws here? Making sense? This is like a quick way of memorizing or pulling back up everything. And now you could use these definitions to describe the laws. Let's see what the question wanted. Pressure versus temperature. So which law is this we're cooking up here? If we're doing pressure and temperature. Pressure versus temperature is which law, people? Pressure law. Volume is constant. So you get this happening here. Now, they want it in Celsius. So sketch a graph of... Now, if they gave you this, you would give them this graph. But if I have to sketch a graph, I would sketch it like this, right? If they ask me to sketch this graph, dry, just so, make sure you sketch it and make sure you put negative 273 degrees Celsius here, 0 degrees Celsius there. We don't know what that is. This is pressure, and this is temperature. This is pressure in pascals, and this is temperature in degrees Celsius. Rate out of 10, how much you all understand that? 10 out of 10? 100. Explain how the graph could be used to derive the Kelvin scale. Listen to this, how you'd put it in words, because most of you all understand what's going on here, but to put it in words. You'll extend the graph to the left until the pressure is equal to 0. The graph will intersect the x-axis at pressure is equal to 0, which is known as absolute 0. This is negative 273. Slower? Now you had to read it with me. You seen it on the screen? Or you have a screen? Yeah. So negative 273 degrees Celsius. This is represented by 0 Kelvin on a Kelvin scale. And the degree divisions equal the Celsius scale. So the degrees 1 degree difference is the same as 1 Kelvin difference. Any questions on this? That's how you change a temperature scale to a Kelvin scale. A degree Celsius scale to a Kelvin scale. So using temperature to represent Kelvin, come up with the mathematical relationship. This is free max. Everybody should know this. T is equal to theta plus 273. Theta is in Celsius. You just add 273. I can't believe they gave 2 marks for that. Physics just giving away marks. Let's go. I'm giving you all a 2-minute head start. Workout B. Yeah, that's what I said, Malik. So you extrapolate back. Did I say extend? I said extending. Or you could say extrapolate. Extrapolate is just a fancy word there. So we're working out part B. Let's go. 2-minute head start on B. You need to calculate the volume. I'll have an exam tomorrow, so act like it. It is actually tomorrow. When it is morning or afternoon? Morning, wow. I know I'll probably make some people hard skip a beat. So I'm just seeing something that next year there may be a removal of SBAs.
What?
And a switch to paper trees.
Yes.
Don't take my word for it, right? You plan on doing exams next year? Or?
Sir, even at our 4th point right now, I'm going to paper sheet.
Well, yeah, they'll probably have the option of doing it. I need to go over, after I finish this live, I need to go and watch over all of these things. Interesting. No, now removal of SVAs makes sense because I mean you might like that, but SVAs is pure nonsense right now. So a container stores 5 meter cube, that's what they do, meter cube of gas at a pressure of 13 atmospheres and a temperature of -23. Calculate the volume. Now the same gas, well, like free max. Free max. Everybody get the answer already?
Yes, sir.
What is it?
I got 78 meter cube.
78 meter cube. So calculate the volume that the same gas would occupy. So you could either do 2 things. You could realize what law is being used, if there's a law being used, or you could just use the full gas law. Most of the times you just use the full gas law and go along on your merry way. Must be equal to P2 V2 like this, and you substitute what you know. If something is being held constant, just remove it. So let's see. Oh, another thing you have to do was accommodate the change of all the Celsius temperatures to Kelvin temperatures. You all remember to do that, right? And you substitute. This is all the first state, 13.5, 250. The second state was 1, 300, and we're trying to figure out V2. You transpose, and you get 78 meter cube. Meritless. M is for meritless, M is for Matthew. Get that already. So, good. Blocks X and Y in figure 5 are identical except for their temperatures. So where will the temperature flow? From what to what? From X to Y. So no paper leaked. That's no why I say I never see any paper leak. I'm hearing exciting things there. Explain the difference in motion of the particles in block X compared to the motion of the particles in block Y. Easy, right? So there is going to come something in the exam. You can take this one down. Who was asking me to predict? Who was predict person here? What's your name? Hannah. Akira. Hannah is the next year. Yeah, so something with kinetic theory should come, very likely. So make sure you know the whole linkage between kinetic theory and explaining anything. What is the kinetic theory question about? So the kinetic theory question is where you associate the kinetic energy, or EK, of the particles in the gas. You associate that with heat, or the temperature of the gas. So the faster they move is the more heat energy they have. So this is what you're going to use for the kinetic theory. Let me see if I find it in the 12-hour crash course. Where is it? Oh no, I don't think I did that. I didn't do that section. So yeah, make sure you have that. So the higher the temperature, the more kinetic energy of the particles. The lower the temperature, the less kinetic energy. The more kinetic energy, the more they ask you to define in the exam, and the more force, are you following? The more force on that particular area is the more pressure, because pressure is force over area. Something like that is going to happen in the exam. Any questions on it? So, you understand? Okay. So watch this. This was a soft version of the question because they asked you to explain the difference. In other words, to tell us why there's a difference in the motion of particles in block X and block Y. X possesses more kinetic energy, so the particles will vibrate more. Y possesses less kinetic energy, so the particles will vibrate slower. The end. In which direction is thermal energy transferred from X to Y? Free maths. Say the condition under which the transfer of the thermal energy would cease, the temperatures of X and Y become the same. Movements. Number 5 is about the DC motor. Are you guys fully equipped to handle any question on the DC motor?
Yes, sir.
All right. So, well, here's a question for you guys. Using Fleming's left-hand rule, because that's what you'll use for the motor, I'm looking at side A to D, AD, A, B, C, D, AD. Will AD come out of the paper or go into the paper? Talk to me. AD, out of the paper or in the paper? I don't see no hands. Use Fleming left-hand rule and tell me, will AD go down into the paper? So your first finger, it's coming up and out the paper, right? So if you're saying down in the paper, that's wrong. It's coming out the paper. Yeah, boy. Hard luck for the Emeritus Day. Or that's or in. So which way will AD go? Will it come up out of the paper or will it go into the paper? So AD, you use your left hand, Fleming's left hand. The middle finger should point from D to A and north to south. So your thumb is pointing up. Now I was showing them yesterday, you don't even need to use the middle finger. You can just do your palm like this. The current is coming out your palm. So D to A is coming from D to A, and this is north to south, so it's going up. And you can check with BC, which direction will it go? Since the current is coming this way, BC it's still going north to south, but it's coming this way, or in other words like this. So it's going down, right? So one is going up, AD is going up, BC is going down. Draw the magnetic field between the poles. I just did that already. State the direction in which dA will move as the upwards out of the plane of the paper. Name the rule which you use, Fleming's left-hand rule. Everybody able to get those marks on mottos if it come? Make sure you put up them gang signs and get them marks, right? Okay. Let's see if you the thingy that the wire is connected to in the motors, what is it called? Split ring. And if you're dealing commutator, split ring commutator, and if you're dealing with a generator, slip rings. All right, good. This is motto. So why is this split ring commutator used? So instead of asking you to describe the whole process of the DC motor, they just ask you straight up, why you use the split ring commutator? What's the definition? It's using DC motors to reverse the direction of the flow of the current through the motor every half turn. This reversal is necessary to ensure continuous rotation of the motor. So it's used to reverse the direction of the current through the coil. Every half turn, it's going to reverse. Remember, we talk about that. Because if it doesn't reverse, when it reaches around on the next side, it will end up bouncing back over to the side, and you would not get a continuous spin. Okay, what is the frequency? They're probably going to ask this in this question anyhow. What is the frequency? Which is 50, you get 50? Mr. Merritt, let's confirm. So calculate the value of the frequency of the generator. T is 0.02 from the graph, that's the period. So 1 over 0.02, 50 hertz. The peak voltage is 100. Calculate the peak value of the current in the resistor. There's a resistor. Oh, yes, father. Oh, yes. Let's see. 100 ohms resistor. So what are you going to use for this one? V equals RI substitute and get your answer. You get 2 amps. Everybody understand this? That's 3 marks, right? The generator is subsequently rotated at twice the frequency. State the effect this will have on the period. So if the generator is moving faster, what would this have on the period? It's rotating twice as fast. The period would half, right? It'll be half. Period will be double. The frequency is double, period is half. And the value of the output voltage will increase. If it's going faster, it's increased. Combined total output voltage will increase. If you want to increase the voltage in the generator, what else can you do? Increase the strength of the magnet and more coils, right? Radium, what's the number of protons in radium here? And the number of neutrons? 138. So they said it's radioactive. Number of electrons is 88. There's no charge, so we just say 88 as well. A radium-226 nucleus decays by alpha. What is meant by radioactivity? That's some kind of circular. So what's your output? The spontaneous disintegration of an unstable nucleus. When an unstable isotope emits particles or waves to become more stable. So I would combine Malik and Kirsten's definition. The spontaneous disintegration of an unstable nucleus, or when an unstable nucleus emits particles or waves to become more stable. Good. Spontaneous disintegration of an unstable nucleus. Resulting in, add this into your definition for the exam. The spontaneous disintegration of an unstable nucleus resulting in the emission of particles or waves so that the atom can become more stable. Yes? Everybody got that? Everybody caught that? So you're using this definition and you're adding on the little extra bit. Everybody didn't catch it. Resulting in the emission of a particle or wave so that the atom can become more stable. Oh, they wanted you to do what type of decay on this? Alpha decay. Which one is the more tricky decay, alpha or beta? Beta, because beta, not too hard, but you have to know that the proton number goes up with beta, right? Alpha decay is just going to minus. You're going to minus the 2 and the 4 from the alpha, like this. Helium nuclei, so it's 2 plus 2, 4. Take it away from this. So this goes to 86 and this goes to 2, 2, 2. Class, are we cooking? Everybody understands that?
Yes, sir.
All right, so this is a lot of information really fast that you hope this is like revision for people and nobody here trying to learn from scratch. Anybody on YouTube learning this from scratch right now? Ariana, behave. Radium-226 has a half-life of 1600 years. What is half-life? We mentioned this yesterday. The activity, right? So the radioactivity to decrease by half. Half-life is the time taken for half of the radioactive nuclei in a sample to decay or to decrease in activity by half. Yes. At a certain time, a sample contains 8. They give us the half-life already, right? It's 1600 years. Everybody, see if you can do this question, Lee. It's 1600 years. Calculate the number of alpha particles emitted by the radium nuclei in 4800 years. That's a tricky question. This is the trickiest way it has come. Everybody attempt this question, please, including the eaters over there. So 8.0, yeah, earlier. 8.0 times 10 to the power of 8 radium nuclei. Calculate the number of alpha particles emitted by the radium nuclei in 4800 years. They gave us earlier that the half-life is 1600. So I could add that in there. Half-life is 1600. Yes, the half-life is 1600. Half-life is 1600 years. Go through. Malik says it's 7 times 10 to the power of 8. Oh my gosh, that's a lot. So if my USB cord wasn't shortened so much, I would show you all the flags around here and ask you all to guess the flags. History man know he flags though. Life is one thing. You got the flags locked.
Sir, how much you need to get? How much you get from paper to get that one from paper?
Anytime somebody asks me that, I mean in problems. I get asked that every. In what? You get 7 times 10 to the power of 8. How much you get? Now, they want the number of alpha particles emitted by the radium nuclei. How many half-lives pass? So 3 half-lives means that this gets half twice. Half 3 times, sorry. So 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. So this has 1.0 times 10 to the power of 8 radium nuclei. But this is not the answer to the question. Usually this is the answer. Usually this right here would be the answer because it's reached to this level. But this is how much is left, right? Everybody understand what I'm saying, the difference? Mm-hmm. So half, 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 half. We're on 1 right now. This is how much is left. But they wanted how much was emitted. Everybody understand? So let's just do a generic number. Let's say it started off at 16 and 2 half-lives pass. What is the value? How many radioactive atoms you'll have right now? If 2 half-lives pass, you started off at 16. You'll have 4. Half-life, you go to 8. Half-life, you go to 4. So you end up at 4. Now, the question didn't ask us how many remain. The question asks how many were emitted. So you'd say 4 from 16 to find how much was emitted. How much was emitted so far? 12. You all understand the difference in the question? I hope you all do because there's a subtle difference there. Where is the question? So 3 half-lives have passed because 4800 divided by 1600 is 3. The number of particles is, and this is a mathematical way of doing it, but you all can do it by hand. You get, this is how much left, and then you take it away to get how much was emitted. 7 times 10 to the power of 8 alpha particles emitted. Alpha particles emitted. How many more time will elapse before the number of radium nuclei remaining falls to 0.5? So if we have to go from 1 to 0.5, that's just another half-life. So how much time will pass? Just 1600 years. Just 1 half-life. 1600 years. Cooking. All right, shout out to the 250 people studying here with us. I am in UWI Mona campus, that's in Jamaica. And I'm here with some students from Campion, right? And some merit listers. End of test. That's 2 exams done so far. Another one. 2021 Jan. Let's go. We're skipping all the question ones. State the principle of moments, class. That's not the principle of moments. That's one of the. That's not the principle of moments. So let's just correct the 2 mistakes. Somebody said one of the conditions necessary for static equilibrium. And that's not the way to state the condition necessary for static equilibrium. He said total upward force equals total downward force. What's the better way to state that? Sum of the net forces in a system, 0 equals 0. That's not the principle of moments. That's just a condition for static equilibrium. What is the principle of moments? And then somebody said momentum. They said the total momentum before collision. So the principle of moments is anti-clockwise moments equal clockwise moments. The total anti-clockwise moments equal clockwise moments. That's a condition for equilibrium. Get the mind map right with this, people. Let's go again. So firstly, I said earlier that people mix up moments and momentum. They have nothing in common. Literally, nothing. And we're still mixing them up. Then moments is part of a bigger topic for static equilibrium. if you go on to do engineering in a place like this, if you go on to do engineering, there's a topic called statics. What you are doing right now, the first part of physics with Newton and all of that, a lot of that is just called statics. There's statics and there's motion. For static equilibrium, there are two conditions. So they can ask you this, everybody's locked in. The two conditions for static equilibrium is, we did this earlier, the sum of the net forces equal to 0 at a point. And for the next thing is the sum of the moments about the point is equal to 0. In other words, the total anticlockwise moments is equal to the total clockwise moments. So these are the two conditions. Moments is just one of the conditions. Class, are you locked in? That's what they ask in the next part of the question. State another condition that is necessary for the body to be in equilibrium. The net force is equal to 0. For example, the sum of the upward force is equal to the sum of the downward forces. State the formula for the moment of a force, providing the meaning of each of the variable and its SI unit. Go through. What's the formula? We mentioned this already. Formula for moments. Matthew.
So the formula for moments would be T equals FD.
T equal FD. And what does F stand for?
F stands for force and D stands for distance.
D is in Newton and Newton meter, right? Cool. When you're describing it, make sure you write distance from the pivot to the line of the action of the force. You can put perpendicular distance from the pivot to the line of action of the force. It's perpendicular to the line of action of the force. Right? So make sure you put that. Throw in the word perpendicular here, right? Everybody catch that last bit? Put, when you're talking about D, put perpendicular distance from the pivot to the line of action of the force. Force, moment of the force. I'll need to lock in. I'll get distracted too easily. Figure 3 shows a girl standing on a uniform plank. All right, the next worst case scenario. It's uniform this time, so what does that tell us? So there's a force acting here. There's a force of the girl acting downwards. This force is acting upwards. This force is acting upwards. We could probably read the scale and get it off, right? Well, you could see that it's higher this direction. So let's go. Let's lock in on this YouTube. Let's see if you can figure this out. The weight of the plank is 270 newtons. So that means 270 newtons is right here at the center, 1.5, right? The plank rests on two scales, 2 meters, equidistant from apart. So if it's 2 meters apart, how much is hanging over on this side? 0.5 and 0.5 would make the additional 1. Everybody understand how this is working? What else? The scales are equidistant from the ends of the plank. The scale reading. This one is 354. Wrong. This one is 354 and this one is 417. And now we need to work out. So I drew everything. They wanted us to draw the forces. I drew it for you. They wanted to calculate the girl's weight. Let's go. Let's go YouTube and calculate this weight. I'm trying to get this thing to zoom less ferociously. Let's go, let's go. Everybody lock in, tell your friends. Tell your friends this is the third past paper we on in 1 hour and 50 minutes. We're going very fast. We should get at least 2 more past papers in. We will probably finish within an hour. That means 9 o'clock Jamaica time, 10 o'clock Trinidad time, rest of the Caribbean time. Somebody said it's 501. Wow, that's very fast. You got that as well? You take moments about where? You just use upward and downward. So upward and downward, 354, 417, 270, upward, downward, subtract, get the answer, 501. Then you need to, so pay attention to that, everybody. When you see that moments question, there is the chance that you start off with upward and downward, not total anti-clockwise equal total clockwise, right? You could kind of tell. How you could tell which one you're using? Yes, this one is usually be less marks. If you're using upward downward, is usually 1 or 2 marks. If you're using total anti-clockwise, it's usually 3 or 4 marks. By taking moments about Q, calculate the grill's distance from the scale at Q. So we need the distance from Q to W. Let's go. Distance from Q to W. Random people taking pictures of me outside of UE right here. But most of the people in UE here would know who I am from previous years. People passing by and taking photos. Like what I do in teaching a random class in UE. Yes, so we have some answers. So those of you all who want to know where the paper, can you all tell them where you can find this paper and the solutions? Right, just type in kerwinspringer.com. Type in kerwinspringer.com. Go to past papers. See all these past papers there? Click physics. You can do the multiple choice, but we're not really on that right now. There are 10 solutions here. There are 44 raw papers. 10 solutions. Click on this. Right now we're on this one. Like yourself. If you haven't seen that yet, you're in for a nice treat. And by the time the multiple choice reach around, you'll see more of these with multiple choice in them. The dots mean there's the multiple choice in them already. The entire multiple choice banks are in some of them. Yes, you heard that right. Have fun. All right, so we have 0.5, a lot of 0.5s in the chat, and we also have a 0.87. Malik said 0.87. We have 2.5s from Kenzie. King Edits. Jade said 0.87. Matthew, where you get? Hasn't finished. Ariana, problems? By taking moment about Q. So you're going to ignore that 417, right? So the clockwise moments will be just the 354 by 2, right? Is equal to 270 by how much? 1. Because it's in the middle, it's 1.5, but 0.5 is hanging off on the next side. They said that. They said these two are equidistant and this is 2 meters. So therefore there's 0.5 on this part and 0.5 hanging off there. So now all you need to do is find W now. Chat, are we cooking? Yes, so W is anti-clockwise, 270 is anti-clockwise. So we have an hour again, people lock in. All right, so let's see how it will look. So taking moments about point Q. Watch this. 501 times D. That's, I have no idea where that is from. Let's go check. Oh, that's the W. Yes. 501. This 501 times D, that's the distance you're trying to find, plus 270 times 1. You see the 1 there, Ariana? I think a lot of people overthinking this question. Why are you all not just mashing it up? Watch what's happening here. Hi, what's up? Oh, you just falling in? You here to study too? Or falling? Oh, you just came back. Oh, I want to know how you walking at the phone alone. I'm like, what, youngster? So We take in moments about here, so this is W times D. Then you have this moment, 270, and this is 1. And the reason we know this is 1 is because it's exactly in the middle here. This distance is 1.5. This distance is 0.5, so we just subtract that 0.5, so we know that is 1. 1 times 270. And then we have this going up like that. So this is 354 times 2. So we just equate that and we solve for D. Everybody comfortable with it now? So I find a little suspicious in the moments question. So let me just give you all a random one now. First, let's see the answer first. So you put all of this, 501D plus 270 is equal to 708. Bring across the 270, subtract. And you get D is 438 divided by 501, and you get the 0.87 meters. So let's slow it down and let's do another question. Let's slow it down and let's do another question. Let's say there's a plank. And the plank is of uniform weight. And the plank is 4 kgs. And we have, let's do a special question. We have Mr. Meritless standing up here on the plank. And let's say he is 30 kgs. So if this question came in the exam, and they want you to get the value of F1 and F2, and W1, and W2. Go ahead. Let's see if how much you all understand. So he has a weight as well, right? So he's W1. W2, let's call him W2. See if you can figure out the value of all of that. F1, W1, F2, W2. I don't even need to tell you the mass, the length of anything. See if you can find the values of all of this. This is a special case. I can tell you that the distance between the fulcrums is equidistant from the middle. So can you do refraction? We did that already. So can you do a graph question? We're doing graph questions. We're just not doing full question ones because I just using up a lot of time. We do a lot of question ones already. So the first thing you can tell me, what is something you can tell me immediately? Which one is the easiest one to find out? W1. You could find out W1 or W2. W1 is what? 4 times 10, which is 40. W2. 30 times 10, which is 300. And since this is equidistant, we could probably work out something. The entire weight of let's remove Mr. Meritless. Let's take him out of the situation. So this is a special case, right? Let's take him out. What would be the force on F1 and F2 if he wasn't there? I'll have to get the sum of this and divide by 2. You agree? The total downward. What is the total downward? 340. So then what would be F1? F1 would be half of 340, which is 170. And F2 would be 170. Now, since he's standing exactly on F1, none of his weight is bared up by F2. So F2 has to remain 170. But F1 will be what? 170. Hold on. This 340 is not supposed to be there. I made a mistake. If it's by itself, if I removed him, this would just be 300, not 340. So this would be 150, 150. And then what will be F1? 150 plus 40, which is 190 newtons. Chat, are we there? Let me take it over. Let me say it again. If we take out the boy, Just the mass 300. What was the boy's weight? Oh, he was the 300. Oh, my bad, my bad, my bad. I thought he was the 40. Yeah, boy, it's not looking good. So the total downward without the boy, or meritless heavy, without the boy is 40. So this is 40 divided by 2 is 20. This divided by 2 is 20. And then we'll add on the 300 here. I'm trying to erase this thing. So is that making sense now to everybody? So you get 320 here. It's making sense now? Let me say it over since I messed it up. So F1, F2, we figured out W1 and W2 really fast. So this is 40, this is 300. I'm saying if the boy wasn't here, this 300 newtons wouldn't be here. I could just evenly split up the 40 newtons between the F1 and F2 if they're equidistant. So this is 20 and 20. But since the 300 newton is standing exactly above F1, that means F1 has to be 300 plus the 20, 320. So if you see in the exam a weight is standing exactly over a fulcrum, that bears the entire weight of it. None of the weight is bared by the other one. Let's do a next. There was an example that came like that a long time ago. Let's do another question. So that was a special case, right? Let's give back these two fulcrums. Let's give the center. Let's make it uniform again. Let's say the mass of this is 40 kg. Let's put a load here, and it's some distance away, and we need to find this is 40 kg. The entire, it's uniform. It's 5 meters long. Let's actually put them at the end. A lot of times they come at the end, which is a little easier to see. And we are trying to find this distance here, x. And I am saying that this has a mass of let's just make up anything, 20 kg. First things first, let's give this, let's do it in reverse. Let's give this. Let's say that this is 1.2 meters. I need you all to find the value of W1, W2, F1, F2. Let's go fast, and then we have to go on to the rest of the paper. So can you do a non-uniform one? Okay, we'll do a non-uniform one afterwards. We did one earlier. Those who just popped in, you could probably pull back and watch it. Yeah, you could pull back and watch the version of the non-uniform that we did. Let's go. W1, W2, F1, F2. What will W1 be? W1 is 400, W2 is 200. Good. So far, so good. So you say W is equal to mg. So W1 is m. 40 by g is 10. So you just put 400. W2, I'm working it out quickly, is 20 by 10. So you get the 200. Everybody understand that? Now you need to find F1 and F2. F1 and F2. F1 and F2 is equal to 200. No, they're not equal. They'll have to be different. F1 is 600, says somebody. F1, no, that's impossible. F1 can't be 600. I can tell if it's right or wrong. Somebody says 350, 250. That sounds kind of reasonable. You got that too? 350, 250. How would you find the value of one of them? You take moments. You're going to take moments. So let's say we took moments about this point. Let's call this point A. Taking moments about point A. What is the clockwise moments we can see here? We can see W2 times 1.2. You can see this moment is coming clockwise here. Class Alicina. Then you can see W1 times this, which will have to be 2.5. And at here, y'all. W1 times 2.5. Ask questions if you all don't understand. Everybody understand this? This is the clockwise moments I'm doing. So these are about point A. These will be making clockwise moments. W2 times this distance, which is 1.2, and W1 times 2.5. No, for those who don't know, who just pop in the chat, I'm live with students here as well. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 students here. And then this must be equal to F2 times 5. How you get the 2.5? Because the whole length was 5. So W1 has to be halfway. It's uniform, 2.5. Any questions? It's making sense? F2 is going this way. This is anti-clockwise. And it's F2 times the whole length of this, which is 5. We actually know W1 and W2. What is W2? W2 is 200 and W1 is 400. So if you multiply 200 by 1.2, yes, you're equating both sides. That's the whole thing. The total clockwise moments must equal to the total anti-clockwise moments. So 200 times 1.2 is what? I'll get many calculators there. 440. 200 times, oh yeah, 240. Plus 400 times 2.5, 1,000. Is equal to 5 times F2. 240 plus 1,000, 1240. And then you'll end up dividing by the 5. So how much is F2? How much? 248. So what is the shortcut to find F1 now that you found F2? Do you have to go back and take moments about this point and find F1? What is the shortcut? Because remember, this is the downward forces, 400 and 200. It's 600, and it must be equal to the upward forces. So it makes sense that F1 would be 600 minus 248, which is 352. Everybody understand that question? This is like mid-level. This is like the method. This is like how it usually would come around this difficulty. It can be slightly more difficult. We did two that was slightly more difficult, especially the one that we did before. Those of y'all who want to do the non-uniform, just pull it back and check back, right? Let's keep going for time. Define the term pressure. How would you define pressure? And then you would give the formula, which is P is F over A. So the only thing I would add in is the word normal. When you say normal in maths and physics, what does it mean? Perpendicular. So the normal force acting on a surface per unit area, you all said that. P is equal to F over A. Write all your units. Cook. SI unit of pressure Pascal in terms of its base unit. So how would you say it Pascal? How would you get the base units for Pascal? Write the formula and get the base units. Pressure is F over A. F is? So is that the base there? Is this the base? Not yet. Not yet. We need to get rid of the N. How would you get rid of N? What formula we could use for force? Mass by acceleration. So this is kilogram meters per second squared. I hear Nelly, I agree with this. Are we on the same page? So I'm going to replace newtons with kilogram meters per second squared. So pressure is kilogram meters per second squared over meters squared. So what do you think will happen to the meters here? I'll end up with 1 cancelling and I'll end up with 1 meter below still. So this is like per meter per second squared. Agreed? So this is what pressure is. This is what 1 Pascal is. Newton divide. Class, we do this a million times. Next, center of gravity. We talked about this. Let me hear your definition. This is a repeat. Center of gravity is? And what's the extra part? For any orientation. For any orientation. Lock in people so you can add in for any orientation of the object here. Describe with the aid of diagram how the pressure in a liquid varies with the depth of the liquid. How does pressure vary? What is the diagram you'll pull out if they ask you that in the exam? Right? And you're going to drop some holes in it. And then what will happen? This one will spread out further. You all know what I'm talking about? So, and then you will mention that this one, there's some force here, there's some force here, there's some force here. So you can name this F1, F2, F3, and you will say F3 is greater than F2 is greater than F1. You all remember this, lab? So what is happening with pressure? Pressure and depth. What is the relationship? Pressure increases with depth. So if you say the depth is H, P is proportional to H. The whole thing, what is the formula for liquid pressure? Rho GH. So notice how H, P here, so the constant is really G. The density and H are the variables. Cool. You say this. I just did 2. I said the force in F2 is greater than F1. The height is greater. It's always going to be 10 for CXC, but they will give you. But it's always 10. They don't ever use 9.8. It's a long time since I see 9.8, but they'll use 9.8 in CAPE physics. So as the depth increases, the pressure also increases due to an increase in the weight of the fluid. Over that point, the weight of the fluid is dependent on the density of the fluid and the volume of the fluid. The volume of the fluid is proportional to the height of the liquid over the point. This is a very full definition of what's happening here. For those who want to see it, it's on my website, cohenspringer.com. The force on the escaping liquid at P2 is greater than P1 and visibly seen by this distance, X2 greater than X1. State the equation for pressure difference between 2 points in a liquid which are vertically distant h apart. They just want you to state the pressure formula in a fancy way. So you'll say change in P is equal to H rho G, but the vertical distance is H, like this. Delta P is equal to delta H rho G. Understood, class?
Yes.
This was a tricky question. Was this including atmospheric pressure? Calculate the pressure. No atmospheric pressure was included in this. Calculate the pressure in pascals due to the liquid column AB, which is 8 centimeters. So, you all want me to do this one or skip this one? Do this one? So we want the pressure. What? It's not very common, but it can show up. So we want if the density of liquid X is, I need to get both of them on the same page. All right, class, hang in there. Let me just get both of them on the same page. So we have this. Then we have this. I think they're asking you something really simple here, you know, it's just looking crazy. If the density of liquid X is this, calculate the pressure in pascals due to the liquid column AB, which is 8. All right, so they just want the pressure right here, which is how we working out that pressure. Just lock into your formulas. Go brave with your formula here, people. Rho GH. So pressure is equal to rho GH. And you substitute and you get the answer. What is rho? Rho is this. G is 10 and H is? What is one thing we need to watch out for here? Yes, they said centimeters, so this is actually 0.08, right? Okay, so we substitute 0.08, 10, 1350. You get that. Where do you get the solutions? The solutions is on my website, kerwinspringer.com. So just go to kerwinspringer.com, this website here. Click past papers, click physics. Here's the paper 2 work solutions. You could get more past papers here, but I have 10 of them with the full solutions. And you have the multiple choice bank here where you can just go and do multiple choice. So you can click on like, where's physics, boy? Physics. I only have 60 questions in physics. I have to go and get some more, yes? And you can do your physics multiple choice. That reminds me, I have to set some more physics. But right now, you all are more concerned in the paper 2 solutions. We are on 2021. We're about to finish 2021. Let's go. So we substituted out. Everybody lock back in. The next one is use your answer in C to calculate the height of the liquid CD, given that the density of the liquid is 900. So we have half an hour again. We have been here for 2.5 hours. We have 3 hours. Half an hour again. What is the height H? How do you find H here? Good. So what they're trying to say is that the pressure here must be the same as the pressure there. So you're going to say pressure is equal to H rho G again, or rho GH, however you are accustomed learning it. But this time the density is going to change. You'll have the new density, and you're trying to figure out H. The pressure we know, we have the density, we have G. We're trying to figure out H. So let's see the working. 1080, was that what we got just now? Yes, same pressure. 1080 must be equal to rho GH. So 900 times 10, H is what we're trying to find now. This is the story of physics right through. Very simple. One equation, find the answer, plug it into the next equation, find the answer. So 1080 divided by 9,000, because 900 times 10, you get 0.12. Now, in this, it may be useful to state, okay, they didn't say the unit, so this is also 12 centimeters. It doesn't matter. Section B, let's go. So this used to come all the time. What they do now is that they switched it up, so they give you all see these types of questions already, right? Where you need to describe how it's preventing heat flow. What are the 3 methods of heat transfer? Convection, conduction, radiation. So they're going to give you something in the exam, like a 50% chance that you get one of these kind of things. There was one with a greenhouse. There was one with a water tank heating system. Yep, that. So, and you will have to describe what each thing is doing to slow it down. So what is stopping conduction here? Which one of these features is stopping conduction? The vacuum, because conduction needs a Medium, it needs to touch. Which one of these features is slowing down convection here? Also the vacuum. Because it needs a medium. Conduction and convection need a medium. So if there's a vacuum, the only thing that can transfer is radiation. Which one of the features is slowing down radiation? The silver walls. What's another feature that's slowing down conduction here, reducing conduction? No. The cork. Why? How is the cork? How is the cork reducing conduction? The material, it's an insulator, so it doesn't conduct heat as easily. So the cork stopper, the cork is a poor conductor of heat. It reduces heat loss by conduction. It also prevents convection currents by sealing the top so warm air can't escape. That's an extra point there. The vacuum stops too one time. As soon as you have a vacuum, you're stopping two things. A vacuum contains no particles or low particle content if it's just a partial vacuum. So heat cannot be transferred by conduction or convection. This greatly reduces heat loss from the liquid. The double-walled glass vessel with silver walls. Glass is a poor conductor, reduces heat loss by conduction, and the silver shiny surface reflection reflects infrared radiation back towards the liquid, reducing. So it does two things. If it's a cold liquid, it reflects radiation this way from coming in. If it's a hot liquid, it reflects radiation from going out. So it's double wall, meaning it's stopping from going in and coming out. So it's reflecting outward and inward. So if it's hot, it will remain hot. If it's cold, it will remain cold. Another experiment like this, but I think we did two already, so I'm skipping this one. That's fair? We did two of this already, the specific latent heat stuff. All right, history placement, say skip that. So determine the mass of the melted ice, then you calculate the heat loss. The chat saying don't skip it, he wasn't here, still looking tired. Let's just quickly go through the idea of what will happen here then. The initial mass was 120, the initial temperature of the water is 35, and the initial temperature of the ice is 0. What is happening? Or is it that they mixed ice and water together? Initial mass of water. The final mass of the water is 140 and the final temperature. Yes. So this one is slightly different. This is another way it can come. There was some water and they put some ice in the water. Method of mixtures. And I think maybe they will want you to determine, yes, so determine the specific latent heat of fusion using that. So that's a method of mixtures. So can you do it? What is the premise that will solve everything in this? There's something that you say when you're solving this.
It's like the heat energy used to melt the ice and convert the temperature, something like that, is equal to like the heat energy gained by the water.
Yeah, something like that. So the heat energy lost, who is losing heat energy? Water, because the water is cooling. So the heat energy loss, everything is right?
Sir, they're telling them that I'm struggling with this is random, I'm picking up.
So the heat energy lost by the water is equal to the heat energy gained by the ice. And how do you, did it go to 0? So the heat energy lost by the water would be easy to find as MC delta theta, right? Where the change in temperature 35 to 18. Everybody on the same page? And how do you determine the heat energy gained by the ice? That one you need two calculations.
The heat energy to melt it and the heat energy to change temperature.
Yes, so you need that heat energy, that MLF, and then you need the MC delta theta. Yes? Good. So you equate those two. So watch it here now. The mass of the ice melted is 20 grams. We figured that out because there's a change in mass. The heat lost by the water is MC delta T, or MCAT, or they like to call it MCAT. We say 120 by the 4.2 by the 17, make sure all our units match up. They did. Grams, joules, Celsius. Celsius. So we get this. This is the heat energy lost by the water. This must be equal to the total heat energy gained by the ice. But the heat energy gained by the ice, I have to melt the ice first, then heat it up. So to melt the ice is MLF, and then the MCAT. This change in temperature is different. It's from 0 to 18 now. Are we locked in? Everybody understand the calculations? So this is going to be 20 by LF. Which one are we trying to find? The specific latent heat of fusion. So we have the 4.2. The only unknown here is the LF. So it's 20 by 4.2 by 18. You get this. Bring this across. Then divide by 20. Where the 4.2 come from? That was given. Any questions? 4.2 was given. They will either give you 4.2 times 10 to the power of 3 joules per kilogram, but it's joules per gram, so it's just 4.2. Any questions on this topic? So there's a high chance that you all will get something with specific heat capacity, whether it's the method of mixtures, also the ice. Yeah, so this is once you know what's going on with this is free maths. All right, let's go. So watch these diagrams. We needed to draw the electric field. Remember I told you all you need to know to draw the electric field? This is drawing the electric field around a point charge. So this one is simple. It's just going in, and a positive will just want to go to that. If it's negative, you just have the field going towards equidistant lines, right? If it's positive, it will go in the next direction. What about if it's plates, if it's flat lines, like if it's negative to positive? We did one like that earlier. The field lines. Right? What about if they did this instead? That's not a positive charge. That represents a charge carrying conductor going in. We spoke about this yesterday. Right, so the X is going in. So how do you draw the field for this? We did this. Right hand grip. So you're going to do the right hand grip. And it's going in. So which direction will it be? Clockwise. And we did when there was this and this next to it. So this one will go anti-clockwise. And then you'll get like something like that. All right, let's see where the question went. The question went with two positive charges. Guys, you'll have to draw more field lines than this, right? This was a kind of lazy drawing here. You'll need to draw more than this to collect the marks. Watch how the different ways this could come. Positive to point charge, you could mix it up. Yeah, it all should go, that's weird. It's not supposed to be skewed up like that. So watch mine, watch my version here. So if a number of electrons transferred from a charge rod to earth through the wire was this and the total charge was that, calculate the magnitude of the charge of one electron. Oh, I thought I was going to bring some cube physics for you all here. How would you get this? So this is a common sense question, people. If you have 4 times 10 to the power of 18 electrons here, and the total charge is 0.64 coulombs, what is the charge of one electron? You just divide. That's like if you say 4 mangoes cost $20. History placement said that. So you divide. So 1 would be 0.64 divided, and you're supposed to get a very tiny number. 1.6 times 10 to the negative 19, which is a number that you should know kind of way, offhand. 1.6 times 10 to the negative 19. Double check it. Moving on, the current that flows through the wire, if it takes 0.40 seconds for all electrons to flow to the earth. All right, current. We want current. What is the relationship between current and charge? And so we have T, we have 0.4. Do we have Q? 0.64. So can you find I? You are going to use one of these equations in electricity. Let's go through all the equations again. We have V equal IR, Q equal IT. Give me some more. IT. No, V equal IT. IR, sorry. Who? I want these simple, quick equations. Look, they're giving me them in the chat. E equal VQ. V equal I already there. E, P is equal to IV. And all the others are just rearranging this. So you can rearrange these in different ways. All the others are just rearranging this. Then what's the equation that you need to know for transformers? All right, but I learned it like this with the P first, Vs, and then IP over I with IS over. So just remember that the I flips, right? Yeah, talk to me. Was that meritless?
Yes, sir.
What's going on? Spencer. Go choose Spencer.
So, sir, it's come to our attention that your formula doesn't seem to be correct.
Which one?
Transform equation.
Transformer.
Yes, sir.
What is wrong about it?
So, as a group,
As a group.
it should be, our group has said that the equation should be NS over NB equal to VS over VB equal IP over IX.
All right, so this is correct as well.
That's what we said to get our answer. I said you are right, sir.
So hear me out.
We said what you have is right, sir.
Both are correct. Both are correct. So if NP over NS is equal to, if I said 1 over 2 is equal to 2 over 4, that is the same as saying 2 over 1 is equal to 4 over 2. So all you need to remember is that the current is flipped to the other one. So what they were saying is that they learned it as NS over NP is equal to VS over VP is equal to IP over IS. That's the same thing. Saying the same thing. So since we're revising electricity again, what are the formulas for the for resistors in parallel? Resistors. And in series. Everybody cooking? So we just substituting Q equal IT here. Make sure you know those 4 short formulas. They're going to use one of them. You get your I. State the direction in which charge will flow if the rod is positively charged. Which rod? If it's positively charged, where would charge flow? State State the direction in which the charges will flow. The charges will flow. How will the charges flow, class, if the rod is positively charged? Can positive charge move? So how will the charges flow? From the earth to the rod. From the earth to the rod. Now, if they ask you what is the direction of the current flow, what would you say? From the rod to the earth. Although the electrons are moving from the earth to the rod, current flow is in the opposite direction of negative or of electron flow. So they didn't ask about current here, they asked about charge. That's a crucial problem. I saw some people in the chat messing up there. How the static buildup of charges on a vehicle could be hazardous. What is the key word you want to bring with this kind of question? No, spark. So the buildup of the charge can cause a spark. And the spark can ignite fluid, flammable, anything. And kaboom. Sudden discharge as a spark when the vehicle touches a conductor or a person. Keyword, spark. Last question. Is this the last question for the night? Maybe not. We'll be able to peep another one. Figure 7 shows the experimental arrangement of the apparatus used to carry out the Rutherfords. Remember I tell you all this could come? I didn't know it now. Let's see. What is the substance that's used on the detector? Zinc sulfide. What type of alpha, shucks, I said it. What type of radiation do you use? Alpha particle. What are the, wait, what is the material in the center here? What type? Gold foil. Why do we use gold? Why do we use gold? Gold is malleable, so we can get it thin. There's like 2 others. It's inert, so it doesn't react with anything else. So we show it's just pure gold there, and has a relatively high atomic mass. High atomic mass. What does that mean? Because it means like it's a big atom, so it'll have lots of space, so you'll be able to see the phenomenon happen. If it was like some kind of aluminum or something there, it would be a little more tightly packed. So the nucleus itself is larger. So these are the 3 reasons why we use gold. It's zinc sulfate we're using to help detect. What were the observations? Two key observations for the GM tube. What are the 2 key observations? So most go straight through. Some are deflected. And what's the thing I said that were deflected? No, there's a little adjective you'll see with deflected. Some are deflected and some are reflected backwards at high speeds. So say high speed. And okay, so those are the 2 observations. Most go straight through, some are reflected, deflected. What does the, other than Ariana, what does most go straight through mean? Hey, other than Ariana. Most of the atom is empty space. And that some are reflected, what does that mean? And 3 things you have to say about the nucleus. Yes, very good. Small, dense, and positively charged. Right? So here you go. Alpha source. So small, dense, and positively charged. Beam of alpha particles going through. Most particles pass through undeflected. Some are deflected, some are reflected back at high speeds. Thin gold foil. This is zinc sulfide. You're good to go. Write the names of the 2 scientists. That was wickedness because real people get this wrong, so make sure you know this. Hans Geiger and Ernest Madsen. Marsden, sorry. I'll remember, make sure and learn these names. Something that you can learn just before you go into the exam. Most subjects have like a learn just before you go into the exam thing. One of the things you can learn just before you go into the exam is the name of the scientist that you need to know for CXC. So, and what they do. So, like, you need to know about Rutherford. You need to know about the whole syllabus. You need to know about Rutherford. You need to know about Newton. You need to know about Einstein. You need to know about these two fellas. Young, yeah, Young. You need to know about Young. What are all these scientists you all know about? Chat. Put them up in the chat. Chadwick, yes. Marie Curie, yes. Aristotle, yes. What are their claims to fame? What do you need to know about them? Yeah, I keep saying Curry. What is it, Curry? What is it, Curry? Nah. What do you all say in Jamaica? Do you all say chicken curry or curry chicken? Curry chicken. Well, Trinidad says curry chicken. Guyana says chicken curry. Yes, Becquerel. Yes. This man don't even know who is Faraday. He thought it ain't looking good by history. Yeah, you need to know about Faraday. Faraday was considered the father of electricity. So you might have to do some research on that. All right, let's keep going. Explain why the experiment was carried out in an evacuated chamber. Oh, by the way, this whole thing is taking place in a vacuum. Why is it in a vacuum?
Because alpha particles can be detected by air.
State the conclusions that were deduced from each of the following observations made from the alpha particles scattered in the experiment. Most of the alpha particles passed through the gold foil and deviated. Most is empty space. A few of the alpha particles were deflected from their path but continue through the gold foil. There's some positively charged region in the atom that repels alpha particles. A small number of... Watch how they split it up into 3 here. Normally we do it as 2. Everybody look at this. And watch how I managed to split it into 2. So they just said some were deflected. So I said there's a positively charged region in the atom that repels or deflects the alpha particles. And a smaller number of alpha particles rebounded. So this is where you're going to use the small, dense, positively charged. It has to be dense and positively charged for it to rebound at that high speed. Describe the Rutherford model. So there was real big on scientists in this year. What is his model? Yeah. So what is the nuclear model? How would you describe it? The planetary model, how would you describe it? J.J. Thompson is the plum pudding.
The nuclear model Rutherford concluded that the atom had essentially dense and positive nucleus.
Right. And
it's being orbited by electrons.
Right. And most of the atom is empty space. So it's basically the same thing again. Everybody locked in?
That's the one that was supposed to explain.
Yeah, that's Rutherford.
And they could ask us any other one.
Yes, they could ask you about J.J. Thompson. They could ask you about who's this guy, by Democritus, or whatever, the atom guy.
He came up with atoms and quantum atoms.
So, which of these symbols here is the alpha particle? Right, so the helium nuclei is the alpha particle. It's missing the 2 plus. The following table shows the mass. So what you expect to see when the mass of the products versus the mass of the reactants? Which one will be heavier, the mass of the products or the reactants? Will the products be heavier or the reactants be heavier? The reactants will be heavier by a little bit. Now remember, when you're doing this, you usually work in what? Use. And what do U stand for? Atomic mass unit. You add up all of that, you subtract, and you get something called the mass deficit. Mass defect, yeah. So when you add up the mass of the products, add up the mass of the reactants are the ones that start off the equation. Eh? These are the reactants here, He and B. You add up that, you add up the mass of the products. There's a difference, the mass defect. Yeah, mass defect. And when you subtract it, you will get an answer in U. And how do you change the answer? How do you change the answer to kilograms? Right, so you're multiplying the n by 1.66 times 10 to the power of negative 27. So here you go, mass of reactants, mass of products. I hope all you're absorbing physics that way. That means all you're learning. Yeah. So mass of reactants, add up mass of products. This is the mass deficit, 0.00605. And then you multiply by 1.66 times 10 to the negative 27. So after you get that, class, after you get your mass defect, you get it in U, you multiply by 1.66 times 10 to the power of negative 27. What's the last step? Yes, equal MC squared. So you take it and put it in M. You don't square that, you square C. Yeah, equal MC squared. That's the last step, yeah. And you substitute. And that brings us to the end of that and the end of 3 hours. So how many papers did we do in 3 hours? 3? However, we didn't do question ones. So YouTube people, how are you feeling about physics? Yeah, don't approximate anything until you reach the end. YouTube people, we're getting ready to rack up the show here. I know there are some teachers who want to go straight down to the wire. My days of pushing straight down to like 4 o'clock in the morning, I think are done. I have enough content on the channel for you all to watch till 4 o'clock in the morning. So any problem, anything that's giving you a problem, you could go learn it. What I want to say is everybody who is here, you should find yourself onto this website, cohenspringer.com, go into the physics, and at least make sure you watch through like 4 or 5 of these solutions. We already did 1, 2, 3. So maybe you can do 1, 2, 3, 4 more solutions and lock it in. So all you want to say hello to the Campion people here.
Ariana's first.
Ariana, come and say hello to YouTube.
Introduce yourself.
Oh my gosh, what's this on this? 397.
397.
My bad, they're all pushing.
So this is our history placement here. Where the merit
Where's
list
the
are.
physics placement?
This is Ariana. Where physics placement.
Physics.
Coming.
Who thumbs down? Who thumbs down?
No, that's me. I when I do this is.
Look out for Matthew Spencer, #1 in physics.
So this is Matthew Spencer, physics placement here.
Orange Sterling.
Number two.
And shout out to the others. See the Trinidad flag in the background, eh? All right, people. Love and blessings. Good luck in exams. Make sure and check out the website, right? Later will be greater.